All right, so in this lesson today, we're going to be learning about inclined planes. So an inclined plane is essentially a specialized surface, okay, at some angle of inclination. So this is the inclination angle, or if you are liking geology, it's known as the angle of repose. Okay. So a few basics about an inclined plane. So an inclined plane essentially is a specialized surface. Again, we have its angle of inclination. I'm sure you are aware that if we were to put a block on an inclined plane and if it was frictionless, no surprise, it would start to slide down the ramp. We also call inclined planes ramps. So why does an inclined plane do this? How come an object can slide down without being pushed? And so we can sort of take a look here. I've got a simulation that will show what an inclined plane does. So right now, as you see, we have a block sitting on a surface. The surface is flat. FG is pulling down and FN is pushing up, equal and opposite. So FG is the blue arrow vector arrow and FN is the red vector arrow. 10 newtons down, 10 newtons up. Nothing's happening. So if we were to change the angle and take this surface and start to move it on an angle, you can see what's starting to happen. FG is still pointed down, okay, but notice how FN is still perpendicular to the surface. And now FN is no longer perpendicular to FG. So something is going on here. If we continue, you can see then that the object slid and it wasn't pushed. So if I was to just play around here and make the friction a bit more, mass a bit more, you'll notice that the angle has to get a lot bigger before the block will move. So notice it's at 22 degrees, the block's not even moving. You can clearly see FG is still always pointed down towards the center of Earth, but we have the friction force, which is parallel to the surface, interesting, and FN, you can see, is perpendicular to the surface. It's almost like weight is fixed going vertically down, and these other two forces are changing as you change the angle. And that's essentially, and there it goes, it slides. So that's essentially what an inclined plane does. An inclined plane causes FG to break into components. We call the first component FG parallel. The second component, we call it FG perpendicular. Notice we use the symbols for parallel and perpendicular instead of writing the words because they're too long to write out. All right, so in your notes package, now we will begin. So this perpendicular force we call FG perpendicular, and the parallel force we call FG parallel. Notice weight is still directed towards the center of the Earth. So as this ramp increases its angle, all right, the value of FG perpendicular and the value of FG parallel will change, but weight will still equal mg. So through some interesting trigonometry, the angle of repose or inclination angle is going to be the same as the angle up here as we go through the second page. So a few things first about inclined planes. Number one, weight always acts vertically, always. Weight is always directly down. Weight is equal to mg. On Earth, g is equal to 9.8 newtons per kilogram. Objects will always move in the direction of the net force. Objects on an angle have a force parallel to the surface, Fg parallel, and a force perpendicular to the surface, Fg perpendicular. Note that Fn is always perpendicular to the surface. That does not change. FG is fixed, okay, and if we have a surface, Fn will always be perpendicular. So if we have a horizontal surface, or if we have a vertical surface, Fn is always perpendicular, right angles to the surface. Okay, so what direction does weight act? Straight down. Force acts on the plane. Parallel force. What force acts against the parallel force? So if we have our object, and if we have FG parallel going down the plane, well, we are going to have an opposing force, as you remember from grade 11 physics, FF, force of friction. Okay, so that's interesting here, and we'll have to talk about the ramifications of this in a little bit. So those are just some questions for you to answer. We'll carry on to the next page. All right, so we are coming back to some trigonometry, which I'll get to in a second. Okay, and moving along. All right, so if we look at our inclined plane, all right, clearly that's the object's going to slide down. So FG parallel, which is actually the third force, FG parallel in this diagram. Force of friction is going up, opposing FG parallel. This would be Fn, okay, which actually is equal to FG perpendicular. Because this component number 2 would be FG perpendicular. This would be the angle of inclination, and that would be the angle of inclination. So what I want to draw your attention to is this triangle right here. Notice that FG perpendicular is the adjacent side to theta, and FG parallel is the opposite side. So this becomes very important in an inclined plane because FG parallel equals FG times sine theta, and FG perpendicular equals FG times cos theta. So that's very important for inclined planes. So I'll put that on your reference sheet. That is your needed information for inclined planes. Another step forward, if you remember from grade 11 physics, is that the force of friction is equal to the stickiness factor between two surfaces, which we call mu. Remember, it's called the coefficient of friction multiplied by the normal force. Okay, so that would be also in play here. And it should be no surprise then that if we've got force of friction is equal to the normal force, it's going to be related to FG perpendicular. But we'll get to all of that in time. So you can see how the diagram was labeled. Don't worry about this. I went a bit extra here, okay? Just the stuff that I'm writing down. All right, so if you want to turn to your second note set, we'll leave this for a second, number 1, on inclined planes and forces notes. If you want to turn to your examples notes, we're going to look at a situation here without any numbers, okay, to show you how we deal with inclined planes. So we're saying that a block is on a ramp, so block there, it's on a ramp, the angle of inclination is 35. So that would be 35 degrees right there. Assuming no friction, this is the simplest case, so mu would be 0, no friction. Okay, we're going to look at the acceleration of the block. Okay, so before we get into this, I want to look at what the inclined plane does to FG. Okay, so FG, remember, is always down. But in purple, I'll show, we have two forces. We have FG perpendicular to the plane, FG perpendicular, and we've got FG parallel. So FG perpendicular equals FG times cosine 35 degrees. All right, and FG parallel would equal FG times sine 35 degrees. Okay, but remember from grade 11 physics, Fg equals mg. So you should be able to substitute mg in place of Fg. So we get Fg perpendicular equals mg cos 35. And it would be any degree, any theta, whatever it would be. But in this example, it's 35 degrees. And Fg parallel equals mg sine 35 degrees. Okay. So we'll draw a free body diagram for the situation. So I'm going to draw it underneath. If we represent the block as a dot there, clearly we've got Fg parallel going down the plane. We've got Fg perpendicular going into the plane. It's interesting to note that the block doesn't fall through the plane here, does not fall through the plane. So we have to have an opposing force, which again is that Fn, the normal force. So note, for inclined planes, Fn is equal and opposite to Fg perpendicular. Now the negative just means opposite. So if Fg perpendicular is going into the plane, Fn would be going out of the plane. So don't worry about actually putting a negative number into a calculation. That's just to show they're equal and opposite. Newton's third law. Okay. So if we go back to our example, if this block is going to slide down the plane, it's going to accelerate. And we know from Newton's second law that F net equals ma. We also know that F net is equal to the sum of forces. So we could then write it like this, where the sum of forces equals ma. Well, if we're looking at the motion parallel to the plane, there is only one force parallel to the plane. And so the sum of forces equal Fg parallel. So Fg parallel equals ma. But we already know what Fg parallel equals because we defined it up here. Fg parallel equals mg sine 35. Again, this will be for any angle between 0 and 90. So we can replace Fg parallel with mg sine 35 equals ma. And the scenario is saying, determine the acceleration of the block. So write an expression. Note the mass of the block is irrelevant. We don't know the block's mass. Look at what we have on both sides of the equation. We have m on the left and we have m on the right. So m cancels out. It becomes irrelevant. It's factored out of the expression. Again, why is this happening? We're assuming this block is not pushed. It's just placed and then it starts to slide, just like in that ramp scenario that I showed you. So if we go to here to reset the system, notice there's no pushing force. So if we just bring the friction down, oh, we'll make it up a bit. There we go. We change the angle. There's no pushing force at all, nothing. Just sitting there, sitting there, sitting there, but the vector components of gravity of weight are changing, and eventually the block slides. So it has nothing to do with the pushing force. The only thing that's making it slide is the fact that this ramp is no longer flat along the x-axis. It's changing its angle. And that is causing weights to change. So an inclined plane takes weight, which is always down, and breaks it into two components, Fg perpendicular and Fg parallel. So back to the matter at hand. Hope you could see quite easily that now we have an expression for acceleration, a equals g times sine 35 degrees. And of course, on Earth, we know that g is equal to 9.8. So 9.8 times sine 35 degrees. In the absence of friction, we can calculate the acceleration quite easily. Make sure we're in degree mode. 9.8 sine 35. And you get 5.62 meters per second squared. And the direction would be down, not down, but down the ramp or plane or incline, whatever you want. So I hope that makes sense to you. What I would do is extend this further. If this is an inclined plane of any inclination, in the absence of friction, U0, object at rest, not being pushed, acceleration will always equal 9.8 sine theta, assuming this is done on Earth. If it's not on Earth, then it won't be 9.8, it'll be a different value. But our ramps will be on Earth, because why would we want to have a ramp on the moon? Okay, so recap. Inclined planes take weights and divide them into two components, perpendicular and parallel. It is the FG parallel that acts down the plane. I would hope you would be anticipating that if there is friction in play, then friction is going to act up the plane, opposite. Likewise, if we had a block on the bottom of the ramp and we tried to push it up, okay, there'd be opposing forces. And again, it always comes down to the free body diagram, which helps us analyze and keep track of all the forces. Okay, so that's our first example. We'll leave the inclined planes examples and switch back and take a look here at what's going on. So hopefully now this makes a bit more sense. We have a 450 Newton trunk. Now that's FG. That's newtons, we already know the weight. So FG equals 450 newtons. It sits on a 30-degree incline, so there's our theta. A, what is the force acting down the plane? P, that is FG parallel. And what is the force acting perpendicular to the plane? FG perpendicular. So if you don't want to turn the page, we'll just go from scratch here. FG parallel would equal FG times sine theta. So we know FG already. We don't need to take mg because we know it's 450. So it would be 450 newtons times sine 30 degrees. I know sine 30 is a nice easy number. Let's pretend we don't know that it's 0.5. So we would take 450 sine 30, and we get 225 newtons. That would be down the plane, okay? And part B for FG perpendicular, okay, would be 450 times cos 30 degrees. Perpendicular force then, FG perpendicular, 450 cos 30 gives us 389, so 390 newtons. That would be into the plane, so that'd be directed into the plane, whereas Fn would be directed outwards, equal and opposite. Okay. So a 54.7 box is resting on a 5-degree incline. What is the normal force? So without a diagram, you can always draw one. We know that the angle is 5 degrees, and there's our block. Okay. I would draw a free body diagram. So there's our block. This would be the plane itself. So now we've got a context that FG perpendicular is into the plane and Fn is equal and opposite. So how do we get the normal force? Well, Fn equals Fg perpendicular, which equals Fg times cos 5 degrees. Now, we don't know Fg, but we do know mass. So now we would go mg cos 5 degrees. So 54.7 times 9.8, we assume it's on Earth, times cos 5 degrees. So 54.7 times 9.8, and we multiply that by cos, times cos 5. And you get 534 newtons. All right. What is the friction force holding the box? So that's holding the box in place. So F net equals 0.
Ms. Robinson, please attend to the office. Ms. Robinson.
So if we look at our FPD for this question, what's pulling the box down the plane is FG parallel. So what's holding it back would be force of friction. So F net is 0. Okay, and we read an F net statement, some forces would equal FG parallel, okay, minus force of friction, which is opposite. If that is 0, force of friction then equals FG parallel. So, which allows us then to establish this. So if we just go mg, it'd be mg sine 5. So that would be 54.7 times 9.8 times sine 5 degrees. 54.7, all in one step to show you. 54.7 times 9.8 multiplied by sine 5 yields 46.7 newtons. So we'll 47. So 46.7. Okay, friction force. Now, if the parallel force is going down the plane, friction must be going up the plane. So force of friction would be 47 newtons up the plane. So that should be a kind of a straightforward example for you guys here. And these are just some solutions. So I will leave these examples for you to work through. I think I've shown you everything you need to know, the basics of inclined planes. The last would be, if you go to the first page, I will give you a text reference in G and Coley. Inclined planes would be pages 94 to 95, only 2 pages in the textbook, 94 to 95. So that will do it for this note set. We look at the examples here. I will go through a solved example for 2A. All right, so a crate of mass 50 kilograms, M, we don't know Fn. Okay, so if you want to save some time, what you can do then is go Fg equals mg and figure that out right away. So 50 kgs times 9.8 newtons per kilogram. You can get your weight pretty quick. So 9.8 times 50, and it's 490 newtons. Okay, good. That might save us some time. The angle is 40 degrees. What is a minimum amount of force to be applied to push the crate up the ramp if the coefficient of kinetic static friction is 0.452? So this is a little bit of a different scenario. We've got our object, it's not a ball, I don't feel like drawing the box. We are actually wanting to push it so that it moves up the ramp. It's not sliding down, it's moving up. So that's our applied force. Okay, so the minimum amount of force, F applied, has to be greater than, okay, or equal to, well, forget the equal to, it has to be greater than the force of static friction. Okay, that's important. But there's something else. If you think about it for a second, if we took this object and brought it to the top, there is a force that's going down as well, and that's Fg parallel. So you have to overcome not only static friction, but you have to overcome Fg parallel. So the force that you have to apply to get this crate moving would be equal to the static friction force added to the Fg parallel. Okay, so now we've built, okay, our statement, and we just can calculate these two forces. All right, so we'll go over here on the left-hand side. Fg parallel equals Fg times sine 40. We already calculated Fg up here, it was 490. Okay, if you didn't calculate it, then you'd have to go mg times sine 40, We found it already. We're going to use the 490. So FG parallel would be 490 newtons times sine 40. And we'll figure that out. 490 sine 40. And that yields 314.96. Okay, so for ease of this, we'll take it to 315 newtons. 315 newtons, and that would be down the plane. Now, friction. Force of static friction equals the mu, the coefficient, the stickiness factor, which is 0.452, times Fn. We don't know Fn, okay? But if you remember, okay, Fn is equal and opposite. There's Fn out of the plane, and it's equal and opposite to, wait for it, you got it, Fg perpendicular. So, mu times Fn, which is Fg perpendicular, which is Fg times cos phi. Oh, so I'll do cos theta at the beginning. So now we just plug and chug. So our mu is 0.452, 0.452 multiplied by 490 times cos 40. So we take 490 cos 40, multiply that by 0.452, and that yields us, okay, 170 newtons. Okay, so now, and that's also, if we're pushing the ball up, or the crate up the plane, this is acting against the motion, which is down the plane. So back to our equation here, F applied, minimum force, is equal to the static friction plus Fg parallel. So we can get our final answer. F applied must equal 315 newtons, Fg parallel, plus 170 newtons, which is static friction. And we can get to our final answer, 170 plus 315 yields 485 newtons. That's the minimum force to move the object up the ramp. So I hope that makes sense to you. Inclined planes aren't too bad. The cos and the sine are always associated, cos associated with Fg perpendicular, and the sine is associated with Fg parallel. So you can try part B. I will put the answers up on my website for that. And I think that is it. So that will do it for inclined planes. If you have any questions, please email me, and good luck with your learning.